This cavitation seminar is presented by the John Brooks Company. We have been providing fluid handling solutions to the Canadian marketplace since 1938. Our products include pumps, spray nozzles, filtration equipment, and valves. Plus, our custom-engineered systems provide fluid handling solutions for a variety of industrial and municipal applications. Cavitation is the #1 cause of pump hydraulic noise. You may have already heard and seen the effects of cavitation, but what is it? Cavitation is the vaporization, or boiling, of a liquid and then the implosive return of the vapor back to liquid. Contrary to popular belief, cavitation is not caused by air bubbles. Here is a vapor bubble collapsing back into liquid. This change in state produces pressure waves of several 100,000 psi and causes damage to any nearby equipment or components. If we are to study cavitation, we must understand why the liquid vaporized in the first place. Let us consider a bucket of water at sea level. There is enough atmospheric pressure being applied to keep the water in a liquid state. We would need to increase the water's temperature to 100 degrees Celsius or 212 degrees Fahrenheit in order to raise its vapor pressure to that of the atmosphere. At this point, the water would vaporize or boil. If we were now to move the bucket of water up a mountain 2,000 feet, the atmospheric pressure would reduce to about 13.7 psi. Now, we would only have to raise the water's temperature to 98 degrees Celsius to induce boiling. So, as we reduce the pressure on a fluid, the boiling point temperature also is reduced. Let us now turn our attention to pumps. If the pump draws too much vacuum, the fluid may vaporize or boil at the center or eye of the impeller. These vapor bubbles are then pressurized as they are thrown internally across the impeller. This causes the bubbles to violently collapse back to fluid, sending out pressure waves that damages the center region of the impeller. The damage can be very severe, as shown here. This is called suction cavitation. It sounds like gravel or marbles are being pumped. To avoid suction cavitation, an NPSH calculation has to be performed. This stands for net positive suction head. There is another type of cavitation that occurs in centrifugal pumps. To understand this mechanism, we must first review the Bernoulli principle, which states, as the velocity of a fluid increases, its pressure decreases, and conversely, as the velocity of a fluid decreases, its pressure increases. Let's take a look at some everyday examples of this principle. As we blow over the top of a piece of paper, the pressure drops, causing the higher pressure below to push the paper upwards. Here is another example. If we blow between two suspended objects, the pressure will drop and the objects will be pushed towards each other. Now let us turn our attention once again to centrifugal pumps. Here is a view of the inside of a typical centrifugal pump. The liquid being thrown outward by the impeller creates a low pressure at its center. This aids in allowing more fluid to be pushed into the pump from the suction piping. The fluid is energized by the impeller and is directed out the pump nozzle by the volute cutwater. If we were now to increase the back pressure on the pump by partially closing a valve, what would happen? We would induce a partial recirculation of the flow back to the impeller. This recirculating flow would induce turbulence. Or put another way, localized high velocities in the fluid stream. If these velocities are great enough, the pressure may drop below the fluid's vapor pressure. Obviously, this would cause the fluid to vaporize. As these vapor bubbles travel back into higher pressure regions, they will collapse back to fluid, creating pressure waves. We will see the resulting damage on the outer portion of the impeller vane. This is called recirculation cavitation. What if we were now to shut the discharge valve completely? This is called taking the pump to shut off. Please be warned, this is not a good operating condition for any pump and can be extremely dangerous. Please consult with the pump manufacturer before performing this test. This shut-off condition causes high pressures to be developed at the discharge of the pump. This will induce similar recirculation cavitation as before, but now the pressures are much higher. This causes the fluid to find an additional flow path to recirculate back into the impeller. This path is between the impeller tip and the cutwater of the volute. The localized velocities in this region again can become high enough to induce a pressure drop below the vapor pressure of the fluid. These vapor bubbles form and then collapse as they travel into higher pressure zones. This is called discharge cavitation. The damage can be seen on the outer tips of the impeller vanes and on the cutwater of the volute. Note, when discharge cavitation occurs, recirculation cavitation will also be present. Let us now compare these types of cavitation with respect to the damage inflicted on the pump. First, suction cavitation. This damages the center or eye of the impeller and tends to send the implosive shock waves down the length of the shaft. Now let us look at the recirculation and discharge cavitation at the same time. The recirculation cavitation occurs some distance from the center of the impeller, which causes a bending moment on the shaft. The discharge cavitation occurs on the impeller vane tips and again sets up a bending action on the pump shaft. This is why we often find premature breakage of shafts when a pump is operating under recirculation and discharge cavitation. Before the shaft does fail, we often see the mechanical seal start to leak as the seal faces flutter under the bending action. Obviously, the larger the diameter of the shaft, with the least overhung dimension, will be most resistive to this bending. This concludes our brief overview of cavitation. Please contact us if you have any questions or would like to attend one of our pump hydraulic seminars. John Brooks is dedicated to the fluid handling market with specific solutions to your pumping, filtering, and spraying needs.